We've been discussing electric charges and electric force, and we often in science, in physics, use gravity as an analogy. People are more familiar, more intuitive about gravity and gravitational attraction and energy associated with gravity than they are about electric charges. Electricity just seemed a little mysterious, I think, which is fine. It is a little mysterious. But we're going to be using that connection between gravity and electricity to talk about a new concept called electric potential and how it's associated with electric potential energy. In order to do that, we have to jump over to talking about some shelves. All right? Join me. Okay. I have here a 10 centimeter shelf and a 40 centimeter shelf, and I'm here on Earth. So if I take a 1 kilogram mass and I put it on that shelf, I get approximately 1 joule of gravitational potential energy more than it had down here. If I have 2 kilograms on that shelf, I've got about 2 joules of gravitational potential energy more. And unsurprisingly, 3 kilograms gives me 3 joules of gravitational potential energy. Now, if I move them up here, this one now has 4 joules of gravitational potential energy above the floor. This, I now have 8 total, 4 and 4, and now I have 12 joules of gravitational potential energy. Hopefully that's not terribly surprising for us. But the new way of thinking about this is, this shelf here on Earth, 40 centimeters above the floor, I can say that any kilogram of mass I put up here is going to be giving me 4 joules of gravitational potential energy. In fact, that's true no matter how much mass I put there. Every kilogram gets 4 joules of gravitational potential energy. I could actually, in fact, call it, if I wanted to, a 4 joule per kilogram shelf. It's not really a common way of labeling shelves, usually just like the bottom shelf or the top shelf or even heights above the ground. But this is really helpful for talking about energy, because I know that as many kilograms as I put up here, I'm going to be getting 4 joules of gravitational potential energy for each. And every kilogram that falls off that shelf will be gaining 4 joules of kinetic energy as it falls. And every kilogram, it's going to take 4 joules of work to put back up there. This bottom shelf can be called a 1 joule per kilogram shelf. And that is because every kilogram of mass that gets put on there here on Earth has 1 joule of gravitational potential energy above the floor. In fact, it's any spot that's 10 centimeters above the floor in this classroom could be called 1 joule per kilogram, that place. Now, it's independent of whether I have any mass there or not. This shelf still is a 4 joule per kilogram shelf. This one still is a 1 joule per kilogram shelf, whether there's mass on that shelf or not. The amount of energy depends on the amount of mass. And so if I take the amount of mass and multiply it by the gravitational potential, which is what we call this, the joules per kilogram, that's called gravitational potential, then the amount of potential energy is going to be dependent on the potential and the amount of mass. Now, the potential doesn't depend on what's there. It only depends on where it is and what is nearby, namely the Earth in this case. If I went to the moon, then this would no longer be a 1 joule per kilogram shelf. Because the moon's gravity is roughly 1/6 as strong as it is here on Earth, that means I would need to be 6 times as tall. On the moon, a 1 joule per kilogram shelf is about 60 centimeters up, about here. Now, that means that if I were to take 1 kilogram and lift it up and plop it up there on the moon, that takes the same amount of work and stores the same amount of energy as picking this up and putting it here on Earth, 1 joule per kilogram. So those 2 shelves with the same gravitational potential, a tall shelf on the moon and a short shelf here on Earth, those are effectively, from an energy standpoint, the same shelf. They have the same potential, whether anything's there or not, as a reminder. Now, if I built a ramp between this shelf and that shelf, I could be confident that no matter the shape or steepness of the ramp, an object going from the top to the bottom would gain 3 joules of kinetic energy for every kilogram of mass that that object has. because I'm going through a difference of 3 joules per kilogram of gravitational potential. The potential difference is 3, well, negative 3 in this case, because I'm going down. So I'm losing gravitational potential, but I'd be gaining kinetic energy as a result. The amount of energy depends on the mass of the thing that is going between, but that is going to be multiplied. Mass times the change in potential is going to be the change in energy, specifically the change in gravitational potential energy. And through the conservation of energy, we know that that's going to be equal to the gain in kinetic energy. Now, how does this have to do with electric charges? Let's jump back to the table and find out. All right, so about electricity. We saw that gravitational potential is based on where you are and what's nearby, but it doesn't depend on what's actually at that location. Whether there's some mass there or not, that shelf still has a potential of 4 joules for every kilogram of mass you put there. Now, what's the connection to electricity? Let's say that I had an electric charge, say a positive charge. Now, nearby that positive charge, other charges would feel a force. They would be repelled or attracted, depending on their charge, because remember that electricity has 2 flavors, whereas gravitational mass only has 1. So, electric charge comes in positive and negative. If I put a positive charge nearby, it would be repelled. It would gain kinetic energy. As a result, it would accelerate away and increase its speed, increasing its kinetic energy. That means that it must have some stored form of energy being nearby another positive charge. That stored form of energy is electrical potential energy. And we can determine how much electric potential energy that object has based on its amount of charge and what's nearby and how close it is to what's nearby. That same idea of gravitational potential. So I could take a spot in space and label it 4 joules of electric potential energy for every coulomb of charge that you put there. That spot right there, this distance away from this charge, would have an electric potential of 4 joules per coulomb. Now, a little bit further away, we'd actually have 1 joule per coulomb. Now, it seems like less, even though we're getting farther away, which feels like the opposite of the Earth. But think about this in terms of energy. Positive charge would accelerate to a higher speed if we start from closer than it would if we started from farther away. So from farther away, it's got less time to accelerate since it starts off farther from the positive charge, which means it must have less potential energy, which means it should have less potential at that location. This location has a lower electric potential than this location. If I take a charge and I move it between 2 locations, I am going to be changing the electric potential energy of that object. And the amount that I'm changing it by is equal to the charge of the object multiplied by the difference in electric potential, or what we call the potential difference between those 2 spots. Now, because electric potential has such an important role in physics, we actually gave it a new unit. Besides calling it the joule per coulomb, we actually call it the volt. So this spot right here would have an electric potential of 4 volts. This one over here would have an electric potential of 1 volt. And so because a difference in electric potential is a difference in a number of volts, we call that a voltage. The difference in electric potential between 2 spots is called a voltage. And so in a circuit, or in a battery, or just around other charges, if you go from one spot to another, and you're changing the electric potential, you're going through a potential difference, aka a voltage. We measure that in volts, and the amount of potential difference multiplied by the charge that's going between those 2 spots is equal to the change in electric potential energy. Now, I said earlier that charges come in 2 flavors, positive and negative. So if I were to have a negative charge here, it wouldn't make much sense to say that this is a positive potential. In fact, we'd have to say that it has a negative potential, negative 4 volts of electric potential at that spot, and a negative 1 volt of electric potential. So that if a positive charge were going from here to here, the way that it wants to go, it would be gaining kinetic energy because it is going towards a negative charge. It would be speeding up all on its own accord because of the electric force it feels. So it would be going down in electric potential because it has to be going up in kinetic energy. Similarly, a negative charge going from here to here would be going up in potential, but would be going down in potential energy because the negative charge multiplied by a negative potential difference, or positive potential, can be a negative change in potential energy. So going down in potential energy for a negative charge, going down in potential energy for a positive charge near a negative charge distribution of some kind. So those are the basics for electric potential. Potential is actually based on location and what's nearby, not on what you put at that spot. And this negative 4 volts is actually true for any spot that's the same distance away from this negative charge here. Any spot that I choose to pick in three-dimensional space that has an electric potential of negative 4 joules per coulomb is going to be the same potential. And we call that an equipotential surface, or in two-dimensional space, an equipotential line. It's just a line that connecting all the spots in the area that have the same electric potential. And we'll learn more about those and how they relate to electric field lines a little bit later on. All right, thanks so much.